Hey everybody, Mr. Garrett here. Just wanted to kind of go through a couple things regarding probability. I appreciate you guys' understanding as going through this, and hopefully we'll have some good news to share here soon. But I wanted to kind of give you some insight into some probability things so that we can make sure you can stay on task and keep chugging through chapter 14 and 15. So this was the practice problems that I had given to you yesterday on Tuesday. And I just wanted to kind of go through these. I think some of these are pretty self-explanatory, but I'm sure some of you had some questions, especially when we get down to like question 2. So this one says American Red Cross says about 45% of U.S. population is type O blood, 40% type A, 11% type B, and the rest type AB. Someone volunteers to give blood. What's the probability that this single donor has type AB blood? So type AB blood is 1 minus not type AB, and then 1 minus the not type AB. Type not type AB is type O or type A or type B. All these little U's just mean or. They're the union. And so we're going to go ahead and we're going to add up the 0.45, the 0.4, and the 0.11 to give us 0.96, and 1 minus 0.96 is 0.04. It seems pretty self-explanatory. However, we talk about notation. Notation is very important. And so showing this is important, especially for a single problem like this. The next one says, has type A or type B blood? We know these are disjoint events. And since they're disjoint events, I can go ahead and add them together. And so a probability type A or type B is probability of type A plus probability of type B. And so that's 0.4 times 0.11, which is 0.511 or 0.51. And then the probability is not type O is 1 minus the probability that they are type O, which is 1 minus 0.45 or 0.55. So all of these events here are disjoint events, which allow us to add their probabilities appropriately and not worry about any intersections, which we'll talk about in chapter 15. Now, the second question, I think people were kind of getting a pretty good idea of. However, we want to get down here, especially with C and D. So the first question says, what are the probability among 4 potential donors, the probability that they're all type O? Well, these are independent events, knowing that as long as the people in line aren't related, there should be no dependence between one and the other. And so all 4 type O means probability type O times probability type O times probability type O times probability type O. I probably should have written that out 4 times. And you get about 0.041. So we can multiply those together because they are independent events, and then we're good to go with that. The probability that no one is type AB is basically saying that we have 4 not AB people. So not AB, not AB, not AB, not AB. We can then multiply all those together. Another way that we could write this is probability not AB. We could say that to the 4th, or we could write it out 4 times. And then we essentially get 0.96 to the 4th, which is 0.849. Now, difference between no one is type AB, that's not AB, not AB, not AB, not AB, and they are not all type A. Now this is starting to get into those combinations that we had talked about the other day. Basically, if we have 4 donors, I'm going to do this on a new page here real quickly. If we have 4 donors, all right, we could have 0. What are we looking at? Type A, 0A. We could have 1A. We could have 2A, 3A, or all 4A. Now, if all 4 are A, it's like check, 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 check. They're all A. And if none are A, then it's 0, 0, 0, 0. So those are like X's. But if there's 1A, that 1A could be the first one. They could be the second one. They could be the third one. That's an X. Or they could be the 4th one. for 2A, that could be a little bit trickier. Let's do the 3A first. So that one's going to be a little bit easier. So 3A's, we could have 1A, not A. We could have A, not A. We could have A, not A, not A. 2A is a little bit trickier. So we go yes, no, no. Yes, no, no. Yes, no, yes. Then we go no, yes, no. No, yes, and no, yes. So there's one way that we can do this. There's 4 ways that we can have 1. There's 6 ways we can have 2. There's 4 ways we can have 3. And there's 1 way we can have 4. And so when we start looking at the question, it says that they are not all type A. Well, this is the only one where they're all type A. So when I do that, if I figure out this probability, which is 0.4 to the 4th, which is 0.0256, okay, all these other ones have, not all A. This is the only one not all A. And so when I do that, probability that they are not all type A is 1 minus the probability they are all type A, and that's 1 minus 0.4 to the 4th, or 0.9744. This one we can kind of look at and say, well, what's the probability that at least one person is type B? Well, remember, at least one, probability at least 1 equals 1 minus the probability of none. Because if we go back to this chart and we change the A's to B's, this one doesn't have at least 1, but this one has at least 1, this has at least 1, this has at least 1, and this has at least 1. And so all, 10, 14, 15 of these combinations have at least 1. This is the only chance that does not. And so this, none, is the complement to these, which is at least 1. And so when I come back here and I say, what's the probability at least one person is type A or type B? That's 1 minus the probability that none is type B. That's 1 minus 0.89 to the 4th, or 0.373. So until we get to binomial probabilities where we'll be able to figure out 2 out of 4 or 3 out of 4 or 1 or more out of 4 or something along those lines, we need to stick with at least 1. This binomial stuff will come into play in chapter 17. Okay, so we'll get to there after the new year. And then the last part, or the last question here, is talking about disjoint and independent. Remember, disjoint means that knowing that one has occurred, the other one can't occur. All right, the intersection of those is 0. So A and B are disjoint if they have nothing in common. And then independence means that if we have the probability of A knowing that B has occurred, does not change the probability of A. All right. Think about independent events having nothing to do with one another. So if we examine one person, are the events that the person is type A and the person is type B disjoint, independent, or neither? Well, for one person, you can't be more than one blood type. So you can't have type A and type B at the same time. That means that they are disjoint events. Okay. Second example says, if you examine two people, are the first events at type A and type B, and the second is type B, disjoint, independent, or neither? Well, now you're looking at type A, which is one thing, and then type B, which is the second one, and you know that as long as they're not related, they're independent of one another. Okay, knowing that this was a type B and this was a type A, that makes no difference. And then, can disjoints ever be independent? The answer to that is simply no. If you know B has occurred, then A can't occur. That influences the probability of A. and therefore they are not